That is working. Excellent. So this is on page 117. 117. Normal rain. Normal rain is actually not pH 7. The pH is less than 7. Why? CO2. And remind me, what did we learn about compounds like CO2 yesterday?
Non-metal.
Carbon is a nonmetal. Okay, so we have a nonmetal oxide. And what do we know about nonmetal oxides? What do? They produce acidic solutions. Okay, so, and what's the other word that we can use for an oxide? An anhydride. So this is also known as, aka, an acidic anhydride. So let's remind ourselves of how you react carbon dioxide with water to get an acidic solution. What do you get when you put CO2 together with water? You get H2CO3. And how do we figure that out? We just take all of the atoms and we smush them into one formula. Combine all the atoms. We have 2 H's, 1 C, and 3 O's. So we get H2CO3, which will then, just like any other acid, produce H plus and HCO3 minus in this case. Okay, and it is this H plus that makes rainwater acidic. Yes?
Does that also mean the smell of the, like, when the rain comes?
Oh, the smell when the rain comes. I feel like that's a lot to do with things that, like, chemicals that some chemicals get dissolved in the water, but I feel that's probably more particles and like particulate matter, like small bits of solid that are dissolved in there. I don't know. So often you'll get smells coming off of the asphalt on the roads.
Yeah.
But, you know, there's also smells in the forest. I don't know. I don't think it's the CO2. I think that is odorless, but I could be wrong. Yes, the answer is I don't know. Yeah. I was trying to think if I could think of it, but I could not. So there we are. Yeah. Now, natural rainwater, unaffected by human activities, can have a pH as low as 5.6. Now, you are expected to know this number. How on earth are you going to remember that? Well, it's not 6, 7. It's 5, 6. So anything lower than pH 5.6 is considered acid rain. Anything down to 5.6 is just considered normal rain, okay? And what causes that pH to be low? It is due to the what in the air? CO2. Excellent. So acid rain has a pH of less than, how much? 5.6. So if rain has a pH lower than 5.6, it is called acid rain. And acid rain is caused by acidic anhydrides. What's another word for an acidic anhydride? Non-metal oxide. Not counting, of course, CO2, because CO2 forms H2CO3, which is not just a weak acid, but if we go look at our Ka value for H2CO3, Ka is times 10 to the negative 7. That's not a very strong weak acid. It's not like up here somewhere, right? It's not like if you had H2SO3 or something like that, which would be much a stronger weak acid. It's a medium to weak acid, okay? So this is a weakish weak acid. And it's going to be there, the CO2 is going to be there whether there are humans or not. Now, can human activity make there be more CO2 and make everything a little bit more acidic so that we can start killing off, you know, corals and stuff like this? Yes, absolutely it can. But the main sources of acid rain are burning fuel, and this, I was pointing out to my other block that generally when you learn something like 1 or 2 days before the test, people usually are like, oh, not so important, right? Because they're like, we just learned it, probably don't need to know it, especially when it's something that's like pretty specific and not sort of a general big concept idea. Well, you might need to know this. So acid rain comes from the burning of fuels, for example, coal, that contains sulfur. It can also come from car exhaust, which produces oxides of nitrogen. So you should know that sulfur and nitrogen are the oxides that produce acid rain. And the reason for that is, can you think of an acid that contains sulfur? H2SO4. Can you think of an acid that contains nitrogen? HNO3. And what do we know about both of those acids? Both of those are strong acids. So they are going to have a much bigger effect on lowering the pH than carbonic acid. So how does this work? So you might have a power plant that uses coal. All right, we're going to draw a lump of coal. Here's our coal. Or other fuels in a power plant. What's coal mostly made of? Carbon, just carbon. Coal is mostly carbon. However, coal contains sulfur impurities. And when we burn things, what are they reacting with? Oxygen, yes? And does it make sense that if we put S with O2, we get SO2? Yeah, okay. So, and SO2 is an acidic anhydride. Now, even worse, what can happen is that you can get, in the atmosphere, SO2 will actually undergo further oxidation. Now, in this particular instance, oxidation means sticking more oxygens on something. That's where the term oxidation comes from. So we take our SO2 and we throw some more O2 at it and we get SO3. Now that is obviously not a balanced equation, so could you please attempt to balance that? If that was not a super easy balance for you, right? Some people may just be able to see it. It's not a super easy balance for me because my math is only, I'm a biochemist, right? What I did is I used my halves, half, because I can look at this and I can say I have 3 oxygen here, I have 2 oxygen here. Really, all I want is 1 oxygen. So I'm going to put a half here, okay? And that a half of an O2 is just 1 O. Now this is balanced, but I won't actually leave it like that. What will I do with it? I'll take the whole thing and multiply by 2. So if you did not find that an easy balance, that is one way to make it easy, is to use those halves. So you would have a 2 and then a 1 and then a 2 as your coefficients. Okay? So the SO2 undergoes further oxidation. We stick more oxygens on it and it becomes SO3. And SO3 is also an acidic anhydride. So now we have not 1, but we have 2 acidic anhydrides. Those being SO2 and SO3. And you can see my glaring error here. Those should not be reacting with oxygen. What should they be reacting with? They should be reacting with water. So let's get rid of the 2 there, get rid of the 2 there, put an H2 there, an H2 there. That means that this is going to be a liquid, this is going to be a liquid, and I need to fix this. So we end up getting sulfurous acid and sulfuric acid. What type of acid is sulfurous acid? It is a weak acid. But if we look at our table of ions, or sorry, not of acids, and we compare it with H2CO3, so here's our H2SO3 and our H2CO3. You can see that it is a stronger weak acid for sure compared with H2CO3. So that means that this sulfurous acid is going to be a problem. However, the sulfuric acid, which is a strong acid, is going to be a bigger problem. Okie dokie. I think that you should be able to write these equations, the sulfur equations. Because they're not that complicated. Yes? Yes.
Should we just remember that entire next batch? The strong acid or how it works?
You should know these up here where you go from S plus O2 gives SO2, and then SO2 plus O2 gives SO3. And then you should be able to do these as well down here. Yes? Okay. And why? Because it is part of the curriculum. Part of the grade 12 curriculum is knowing how acid rain works. Yes? Now, technically, you should also learn the equations for nitrogen. But I promise you I'm not going to ask you that because the equations for nitrogen are more complicated. And I think that is not worth your while to remember that. So, we had our coal with the sulfur impurities. That's one source of acid rain. Another source of acid rain is cars. Yes? So what's going to come out of here? NOx. So in the hot cylinders of an internal combustion engine, you still have air, and what is air mostly made of? Nitrogen. So there's going to be nitrogen in there, and it is going to react with the oxygen, and you're going to end up with some sort of NO compound. And so what can happen is you can either have two ways to get nitrogen oxides. You can get N2 plus O2 gives 2NO, and then 2NO plus O2 gives you NO2. Or you can go straight from N2 plus O2, 2O2 goes 2NO2. Both ways will work. That's why I'm saying don't worry about memorizing them. Just know, where do these come from? They come from cars, internal combustion engine. Obviously, if you have an electric vehicle, no problem. You won't get this. NO2 is acidic and hydride. So nitrogen dioxide then reacts with rainwater or the cloud droplets to produce. And again, this is one of these equations where it's not just cram them all together and make one formula. So I don't expect you to know this equation. You get nitrous acid, which is weak. So that is and I think is it relatively strong? Let's take a look. HNO2 times 10 to the negative 4. That's not as weak as like times 10 to the negative 7, right? So this is a problem. But we also get HNO3. And because HNO3 is a strong acid, that is a bigger problem. Is good? Okay. There are also other ways of getting acid rain that are not caused by humans. So natural causes of acid rain. If you have a volcano, you know how volcanoes smell like sulfur? Because there's sulfur in there. They often can produce SO2 and they toss that up into the atmosphere where you are going to get, what are the two acids you're going to get from this? You're going to get H2SO3, and then this will become SO3, and that will give us H2SO4, okay? So that's one way you can get acid rain just naturally. And then lightning can actually cause enough energy just in the regular atmosphere out there for the nitrogen and the oxygen in the atmosphere to form NO2. Okay, and from there, you're going to end up with HNO2 and HNO3. Now, it turns out that there are some places that are like, acid rain, we don't care. What do you imagine is present in those environments? Base. Okay? And the particular base is usually, so we have some rocks and soils that contain carbonate, CO3 2-. And what kind of a thing is CO3 2-? It is a base. Okay, and it will neutralize the acid. So, could you guys please write the results of this neutralization reaction? What do we get? Remember, combine your outside ions, combine your inside ions, we get H2CO3 and CaSO4. Now, you should look at H2CO3 and say, oh, but I know something about that one. What do I know about that one? What does it do? It turns into carbon dioxide plus water. Okay, and then you'll still have your CaSO4. And the reason that is important is because although this is a one-way arrow, this really truly is actually an equilibrium, but because this is a gas, it escapes, which causes carbon dioxide concentration to go down, which causes the equilibrium to shift to the right, which causes more of the H2CO3 to outgas as carbon dioxide, and it just keeps going and going and going as the carbon dioxide escapes. Yes? Okay. So sometimes if you get a very acidified lake, they will just dump some powdered limestone in there. Limestone is just calcium carbonate, okay? But this process is expensive, so that's why it is not like an overall really great solution, okay? Now, what are some problems associated with acid rain? Technically, this is also part of the curriculum. You should know at least a couple. I usually pick the first two because they're pretty easy to remember. What is acid rain going to do to aquatic life? That's going to be bad for it. Look, aquatic life is affected. You don't even need to say what happens to it. It's bad for it. Yes, bad for things living in water. What about forests? Is it good for forests? No, they get weakened, possibly killed. All right, and then there's a bunch of other things. Minerals can get leached out of the topsoil, and you can end up with them moving into lower layers where the plants can't get at them. And also aluminum 3+ ions are released to fish and plants. That's bad for them, can kill them. Metal and stone buildings and statues, especially marble, which is calcium carbonate, they can get damaged, okay, because it will just eat away at them. And if you have high smokestacks, you know those power plants that are burning the coal, acid rain can actually travel large distances. So you might have a smokestack on one end of the world causing acid rain in a totally separate part of the world. So, how can we solve this? Well, they have international conferences and agreements to limit sulfur in fuel. So they're trying to get the sulfur out of the coal before they burn it. And trying to get the NO, whatever it is, out of the car exhaust. Alternately, you might say, instead of using burning coal, let's use geothermal, let's use solar, let's use wind. Pulp mills used to use sulfites, but now they use hydrogen peroxide. So if you have industrial processes making these things, let's update them. If you have a smokestack, before the smoke gets out, you might have like just a little thing in there that's filled with calcium oxide. And as the SO2 comes up through the smokestack, it passes through there. I would assume that this is heated. You know, they're going to have some sort of like, thing. They heat it, and guess what happens? It reacts with the calcium oxide, and you get CaSO4. No longer non-metal oxide, no longer acidic. Yes? Okay. And then you can recycle things. I don't know. Yeah, there we go. Okay, so that is acid rain. And I think that is it for regular chemistry. Acid base. Yes? Are we done with acid base? You're going to come get a new book. Oh, new answer key. AP extras. Nice. And we're going to start on page 1. Okay, so we're going to get out of the regular Chem 12 world of, we have a weak base and the salt of its conjugate acid, therefore it must be a basic buffer. We're actually going to calculate the pH of buffers and figure out how to choose a weak acid, weak base combination that will give you a buffer of a particular pH. Okay? Now, you can solve buffer calculations by using, I should have said 3. There are 3 methods of calculating the pH of a buffer. Number 1 you can use a Rice table and Ka. Number 2, you can use a rearranged Ka expression. And number 3, that should say 3, not 2, because we can count in this class 1, 2, 3, not 1, 2, 2. We can use the Henderson-Hasselbalch equation, which I love that name. It's fantastic. I guess it was made by Mr. Henderson and Mr. Hasselbalch. Okay, you can just call it the HH equation, okay? So let's do the one we are most familiar with. Let's do our Rice table and Ka, and then once we've done the Rice table and Ka, we're going to see why just using a rearranged Ka works, and why we can just make an assumption and just skip the Rice table and go straight to the Ka expression. All right. In this particular instance, we are going to be looking at an example where the weak acid and the weak base concentrations are equal. When this is true, we say that they are equimolar. You should know that word because sometimes in questions it will say you are given an equimolar mix of a weak acid and its conjugate base. So you should just know that that means they are the same molarity. Okay, equimolar, equal molarity. And we're going to do this because this is the simplest case. This gives us the simplest formula. All right? So we have a buffer solution, and it is going to contain 0.5 molar acetic acid. And it's going to contain 0.5 molar sodium acetate. And what we are going to do is we are going to write the acid dissociation for the acetic acid. So we have our acetic acid, 0.5 molar. We have our acetate ion, which is also 0.5 molar. And then, of course, we have our hydrogen ion. Could you have written this with water in the reactants? Yes. I didn't just because I think I wanted to save some space. Okay? Because we start with 0, H plus, that means this must be shifting to the right. And so that means that, of course, our products are going to go up and our reactants are going to go down. So we end up with acetic acid 0.50 minus X, 0.50 plus X for the acetate ion, and then just X for the hydrogen ion. But what do we normally do when we have these X's here? We assume X is insignificant. And if we assume X is insignificant, and let's take our Ka expression now. Let's plug in our 0.5, and our X. Well, if we're like, no, we don't need that little X. No, we don't need that little X. Right? We don't need those. We don't care. Then what happens with our concentration of the acid and the base? They cancel out because they are the same. Yes? And so that means that X is equal to 1.8 times 10 to the minus 5. What is X? concentration of H. What is 1.8 times 10 to the minus 5? Ka. So what do we have? Ka is equal to H plus, or H plus is equal to Ka. Have we seen anything like this before? Yes, we saw it both in indicators when we were at the transition point, and we saw it in titrations when we were at the half equivalence point. And if you remember, at the half equivalence point, what can you say about the moles of the acid and the base? They are the same. So this is the same thing. That's why that's in that buffer region. It is exactly the midpoint of the buffer region, and so we are dealing with exactly this same situation. Okay? The only thing is, in a titration, we have made that buffer by adding, say, a strong base to a weak acid. And in this case, we just added sodium acetate to the weak acid, and that's how we got our weak base, rather than neutralizing some of the weak acid. Okay? But no matter, it works out the same. And what we end up with then, if we want to find the pH, obviously we take the negative of the log of hydrogen, and that's 4.74. Because this solution has a high concentration of both the weak acid and its conjugate base, it will keep the solution relatively constant at a pH of 4.74. So what this means is that for a buffer, for an equimolar buffer, pH, or sorry, H plus, oh, why am I writing it? It's right here. H plus is equal to Ka. And if you take the negative log of both sides, you end up with pH is equal to Ka. So you can use your table of acids and their Ka values to pick a good choice for an acid to make a buffer out of to get a certain pH. Let's go take a look at our table of acids. Okay, and we were just looking at acetic acid, which is here. There's acetic acid. And you'll see that it is 10 to the negative 5 is the Ka. What was the pH at which it buffered? 4.74 or whatever it was, like really close to 5, yes? So if you wanted something that was going to buffer at, say, pH 6, what might be a good choice? H2CO3, because even though there's nothing up here that has a 6, right? Nothing has a 6. But the fact that this isn't 1, it's actually, some distance away from 1, it's bigger than 1, and we've got 10 to the negative 7, then it's going to be 6 point something, right? So if we actually, could you guys find the pH of a buffer made of H2CO3 and HCO3 minus, if they were equimolar, if we had the same number of moles of each? Could you please find the pH of that? Yeah, we get 6.36, okay, or 6.37. And that's all right, that's pretty close. We can actually get even closer by making the concentration of acid and concentration of base not exactly the same. Okay, we can work out what the ratio between those two would be to get even closer to pH 6. And that's what we're going to be learning how to do next. Okay? And you can actually say, okay, what if I had, what if my acid were H2O2? That would actually buffer at about pH 12. Is that an acidic buffer? No, even though it would be made from an acid and the salt of its conjugate base. So do you see where the regular Chemistry 12 curriculum is limiting in what we teach you about it? Whereas, if you had HCN and NaCN, you would be buffering at about pH 10. So that, even though it's a weak acid and the salt of its conjugate base, that would be a basic buffer. Yes? Okay. So I don't like the fact that they limit that, but, there's only so much time in the curriculum and I can't teach fast enough to teach that to the regular classes. So there we go. But you guys can learn it because you're geniuses. Yes. All right. Okay. Now, with the use of log rules and a bit of manipulation, we can broaden this to cases when HA does not equal A minus. Okay? So we can take our Ka expression and we can solve for H plus. And we get this formula here. And you can just use this formula. Yeah? So this is just rearranged Ka. And you can just use this. And what this does is we ignore change in concentration, and we ignore the change in concentration. In other words, we're assuming X is insignificant, and we're jumping straight to that without even doing a Rice table. Are you good with that? Okay. So we just are like, Rice, X, don't care about them. Not so important because we know with buffers, the concentration of the acid and the base have to be quite large. So what are the chances that the X is going to be significant to these quite large numbers? Not very, okay? So you can just ignore the Rice and the X, and you can just say, I'm just going to solve this for H plus. Okay, and this then, we've taken this, which is true when the concentrations are equal. What was that? Oh, it drew an arrow for me. I did not want an arrow. Okay. So we've taken the H plus is equal to Ka, which is true if HA and A minus are the same, because if they are the same, then this term just becomes 1, right? And we can then plug in other concentrations. Now, what if we didn't want to do this? What if we wanted to go straight to pH, right? Well, we know that for an equimolar situation, pH, we knew that pH is equal to pKa. So it would make sense that when those two concentrations are not equal, that pH would equal pKa, and then there would be some sort of term at the end that makes it either go up or down a little bit. Yes? Does that make sense? Okay. So we do some math. You don't need to know how to do the math, but I'm going to show you anyway in case you're interested, okay? So you need to know the following log rules. Log of m times n is log of m plus log of n. Log of m over n is log of m minus log of n. And you need to know that log of m to the power of k is equal to k times the log of m. I never remember that one until I see it here, okay? So I would not be able to derive this myself, but you guys are probably fresher on logs than I am. Anyway, so we want our pH is equal to pKa, but with our extra terms. So we're going to take the negative log of both sides. So we've got negative log of hydrogen. So we're just using this equation up here, and we're taking the negative log of the whole thing, and then we're taking the negative log of the Ka times HA over A. That gives us negative log of H equals negative log of Ka minus the log of, and then the negative log of HA over A. This is just pH. This is just pKa. And now we are going to just play a little mathematical game. All right. What we're going to do is we're going to take this term and we're going to flip it upside down. Okay? But because we aren't really doing anything to anything else, we're going to flip it right side up again by putting a -1 there. Isn't that irritating? This is why I didn't study math, because they just do weird things all the time. I'm like, why would you do that? But you can, because if you remember, log of something to the k is equal to k times the log of something. Yes? So this is going to multiply that negative sign, which is going to turn it into a positive sign. So we're going to end up with pKa plus the log of the base form over the acid form. Do you need to know how this happened? No, you do not. This is called the Henderson-Hasselbalch equation. And could they have just done minus log of the acid form over the base form? Yes, they could have, but they don't. Okay? And this is the format that you are given in the AP data booklet. So let's go look. AP data booklet. Nope, not that one. That one. This is in the section titled Equilibrium, which is on the back. Usually the stuff on the front is kind of like the grade 11 stuff, and then this is kind of like the grade 12 stuff because we got kinetics and equilibrium and thermodynamics, right? So on the back we have equilibrium, which includes all of our acid stuff, and you can see we have pH is equal to pKa plus the log of, whoops, what happened? Where'd it go? Come back. There we go. Aha. So, can you use this equation? Absolutely. You do not need to derive it. You can just grab it from here and say, excellent, I'm just going to throw things in there and I will know what I get. Okay? All right. And remember, this formula ignores the change in concentration. So the minus x is just gone. Yes?
Why do we need to make it positive? So we use the answer to negative log HA.
Mr. Henderson and Mr. Hasselbalch thought plus is better than minus. I don't know. Right? Who knows why they do things? Why did they make the electron negative? That screwed everything up. Well, they didn't know any better back then. They randomly assigned them. They said, the electron is negative. The proton is positive. And that made everything just bad. Bad, bad, bad. That's why we have conventional current now and all kinds of stuff. And they thought it was positive charges that moved. And anyway, doesn't matter. They should have made the electron positive and the nucleus negative, but they did not. So there we are. Stuck with it now. Now, because these are concentrations, and they're per liter, but because a buffer is all in one solution, so the volume is all the same, you can actually use moles and moles if you want to. Yes, because the moles will end up being the same because the volume is the same. Yes? So if it's more convenient, like if they give you moles instead of molarity, you can just chuck moles of the base over the moles of the acid. But that's, if you remember to do that, that's fine. If you don't, just use concentration over concentration. All right. So here is the Henderson-Hasselbalch equation, or like I said, you can use Ka and just rearrange it. Yes? Or you can even just use the Ka expression, not rearrange it, and just chuck everything in and solve for H. Chuck your numbers in and then solve for H. That's also perfectly fine. Okay? So, let us try looking at all our ways of solving it with a problem where the acetic acid at 0.5 molar and the sodium acetate at 0.4 molar, where those are different. Yes? And we can do if you had to predict, do you think you would get more hydrogen or less hydrogen if we have less CH3COO minus to start with? I personally think we're going to get more because we've got less stuff pushing back that way. We have the same amount of stuff pushing that way and we have less stuff pushing that way. But we'll find out if I'm right. I don't know for sure. That's what it feels like to me. Let's find out. Okay. So we have our Rice table. We're assuming X is insignificant. And so do you see why this Rice table is kind of unnecessary? Right? Because we don't need to deal with that. We just need to say hydrogen is unknown, and we know the concentration of that, and we know the concentration of that, and we're done. So that's kind of unnecessary. So you can just chuck everything into your Ka expression. You don't even need to use the Henderson-Hasselbalch equation. You can say Ka is equal to that. You can plug in your base. You can plug in your acid concentration and just leave H. Solve for H. And then you can find your pH. pH is equal to 4.65. Was I right? Did we end up with more hydrogen? The original pH was, when it was equimolar, the pH was 4.74. I was. See, 35 years doing something, you pick up instincts. Excellent. Okay, or you can do the solving first. You can say, okay, I don't want to move everything around with numbers. I just want to solve for hydrogen first. And then I plug everything in. And I get the same answer that I did before. Yay! Or there is the Henderson-Hasselbalch equation. pH is equal to pKa, which is the negative log of Ka, plus the log, and we put our base concentration over our acid concentration. And then we get the log of 0.8. So this is the equimolar pH. And this is our adjustment. Is good? I kind of love this. Even though like you're given the Henderson-Hasselbalch, like you also know Ka, right? And it's pretty straightforward, so you can do it that way as well. All right. Because pH equals pKa plus the log of AHA, should you have to remember it, you can just use the log of AHA. But lots of people remember the Henderson-Hasselbalch equation because it is pH plus pKa equals the log of Ba, where this is the base and this is the acid. And I decided to keep it in because I found a picture of a sheep holding chemicals. And so I thought, oh, I could just toss it out, but I have trouble saying no to something like this. Because look at him. Isn't he cute? Log of Ba. Okay? This is the acid form of the Henderson-Hasselbalch equation. Can you guess what the base form of the equation is? POH equals pKb plus the log of A over B. So you just switch everything, yes? So should you be given a Kb value for a base, this formula might make a little more sense to use, yes? Although you could also just use the Kb formula, right, and solve for OH. If you know the acid form of the Henderson-Hasselbalch, you should be able to figure out the base form. And could you find the pH of a buffer solution consisting of 0.035 molar NH3 and 0.05 molar NH4 using the acid form of the Henderson-Hasselbalch equation and then using the base form? Could you do that, please? Hi. Who have we got here? Where's she? Yes, she's here. Thank you so much.
I like it.
Did you get pH 9.10? Or are you still working on it? If you've finished finding the pH, let's find the pOH. Mm. I would never solve this problem this way unless they gave me the KB, because otherwise you're having to calculate it using KW over KA of NH4. Yeah. And that gives you your KB. But we're just proving we can do it. Yes? Does that make sense? And you notice that our pH and our pOH equal 14, so that is correct. Yes? And that's as far as I got with my other block, because they asked a lot of questions on the review. So your homework, let's make sure that you get some review on acid rain and anhydrides. So 5.7C. Okay. 5.7C. And how about a couple of other problems? On the page 6 in the white book. Page 6, number 1 through 3. Okie dokie? There you go. Yeah.
There's so much fun in TV, right? Yes. Yes. No. You just gotta do it. Same, but thank you. Scale the same. Average. Yeah. Yeah. Yeah, we got two planes right and there looks around. But this one back there. Yeah. Sorry? Yeah. Yeah. I should remember to do that. Absolutely. I gotta go get dragging.
Also, do something on it.
Oh, yeah. Yeah. I would say. All good. I'll make sure that's right for you.